Hello, in this video we will talk about the angular momentum of a rigid body in rotation. In the previous video we talked about particles or a system of particles rotating or not, and we defined how to calculate the angular momentum. The angular momentum was just r cross p or r cross mv. We saw that this was good for what single particle or a system of individual particles in which the angular momentum of a system was just the total angular momentum, total or system, as you may want to call it, and then you just add all the angular momenta, right? Particle 1 plus particle 2 plus and so on. Today we're going to talk about a rigid body. So here, for instance, you could have one particle or many particles would move with respect to each other, so the system can be deformed. But if we talk about a rigid body, then that doesn't deform. Let's start with the simplest rigid body there is, which is a disk. So to find the angular momentum of a disk, what we will say is we'll take this particle here, just a little tiny particle of the disk, and calculate the angular momentum of this individual particle. So it will be the mass, its velocity, and its position, right? Remember that this is in circular motion, so in circular motion v is r omega. So instead of v, I'm going to write r omega, and then there's another r. And what we get is that the angular momentum of this little tiny particle is m r squared omega, right? If we want the angular momentum of this system of particles, then we will need to find the system or the body, right, will be the sum of all the individual angular momenta. So will be the sum of mi ri squared and omega I, right? And then we do all of that, and we add everything. Well, we're gonna recognize that the angular velocity is the same for every particle. So this is just gonna be the mass and the position of each particle times omega, which is the same for everybody. And if you remember, this is equal to the moment of inertia. So what we discover is that the angular momentum of this thing is the moment of inertia times omega. There you go. So it's angular, it's a vector. Compare this to the linear momentum, which is mv. You see, linear momentum, angular momentum. Linear velocity, angular velocity. Linear inertia, angular inertia. So same equation, right? But the angular version of it. Remember, this is a vector, so in this case, this will be in the z-axis, or you can put it like k. Use your right-hand rule, and you're going to find the direction of the angular momentum of the rigid body. So depends of what is the moment of inertia and what is the angular velocity. And the moment of inertia, remember, changes with respect to where you put the axis of rotation. So does the angular momentum. The angular momentum of this disk is not the same about this axis or about that axis or about that axis, because the moment of inertia is not the same either. So we said that torque, if you remember from that Newton's second law in angular terms was this, right? But so we're learning that the torque is, well, the first derivative of I omega, right? So this is going to give us I d omega dt plus omega di dt. That's the torque. But I is constant, so this doesn't exist. So what we get? That the torque is I, and what is the omega of the dt? Well, I alpha, which is something we knew from a previous chapter, previous videos. When you look at this equation, it's telling you you need an external torque to accelerate this mass. If you look at this from this perspective, is you need an external torque to change your angular momentum. So let's talk about this example. A father and a daughter, MF and D, sit on opposite ends of the seesaw. Equal distance from the pivot. It's there. We are going to model the seesaw as a rigid rod. Mass capital M, length L, no friction. So the combination rotates in a vertical plane, so in this plane, and angular speed omega. So find the angular momentum. Okay, so the angular momentum then will be the moment of inertia of the father, the moment of inertia of the daughter, the moment of inertia of the seesaw. It's like saying the total mass is the mass of the father, the daughter, and the seesaw. So if we remember for a rod, the moment of inertia of a rod about its center was 1/12 m, and then the L squared. The moment of a particle was mr squared. So that's what we're going to do. For the father is going to be the mass of the father. The distance that the father is with respect to the center is L/2, but that we have to put square, right? The daughter, the moment of inertia of the daughter will be mass of the daughter. Its distance with respect to the pivot, which is half the length, and then the moment of inertia of the seesaw, well, is 1/12 times the mass of the seesaw, which we said is m, and then just its length, which is L squared. There you go. So from here we can factor a little bit the L squared. Okay, and then we're gonna have L squared that affects mf/4 plus md. I don't know why I put it, and because this is a 2, it's ugly, 2/4, and then big M/12. So we can probably do a little more here, factor the 4, and then we get mass of the father, mass of the daughter, and mass of the seesaw over 3, and that's a moment of inertia. So they want the angular momentum. So the angular momentum is just I omega. So L will be I, which is all that. Okay, I'm gonna write it again. Mass of the daughter, mass of the seesaw over 3 times omega, and that's it. That's the answer. Why? Because they did give us omega. And they gave us all the masses. So you see, the angular momentum is expressed in terms of everything else they gave us. So now there is question B. Find an expression for the magnitude of the angular acceleration of the system when the seesaw makes an angle theta. So, as we can see in the same drawing, at this angle theta, there is net torque on the seesaw because this force, the weight of the father, is larger than the weight of the daughter. So what we can do is add all the torque around the pivot O. So that's going to be the torque, positive torque because of the father, minus or plus actually the negative torque because of the daughter. Notice that the father makes the system spin clockwise, but right, so that's positive as the torque because of the father, but the daughter will try to make the system rotate counterclockwise. I said that backwards. Counterclockwise the father, clockwise the daughter. So the torque due to the daughter is negative. And that's what I put here. And of course, those two together must be equal to I alpha, right? So all we have to do is find the torque because of the father, and then add the torque due to the daughter. So remember that to calculate torque, what we want is the perpendicular force to the lever arm, which is here. Same thing here, we want the perpendicular, oops, that's ugly, the perpendicular force, right, here. So look, you need to understand that this horizontal is 90 degrees from the vertical, and that the seesaw angle is 90 degrees with respect to this perpendicular direction. So that means the angle theta is there. So I can decompose like so, right? Do you see how this is mg cosine of theta, and this is mg sine of theta? So to find the torque of the father is r cross p. That is, sorry, no, not r cross p, r cross f. R cross p is the angular momentum. R cross f, yes, is rf sine of phi. But in this case, sine of phi actually gives you or f sine of phi is also phi, by the way, will be all that. But it's also, this is the same as rf cosine of theta. Remember, r or f sine of phi gives you the perpendicular component of the force with respect to this, to the lever. But if I do f cosine of theta, it's also giving me the perpendicular component as we saw before. So that's the torque, right? The torque of the father, I just have to put the torque of the father, then is the r, which is L over 2, the force, which is m father g, and then cosine of theta. And that's positive. The torque of the daughter will be the same thing, L over 2, mass of the daughter g, cosine of theta, right? So the net torque then is, well, m father g L over 2 cosine of theta minus mass of the daughter g L over 2 cosine of theta, or g L over 2 cosine of theta mass of the father mass of the daughter. That's the net torque, and that's I alpha. So alpha then is the net torque over moment of inertia. So that's g L over 2 cosine of theta, mass of the father, mass of the daughter, over the moment of inertia, which is all this. So L over 4, L squared, mass of the father plus mass of the daughter plus mass over 3. And then, yes, you can cancel one of the L's, and then that's pretty much it. There's also the 4 and the 2 to do something about that, but when you combine everything, you're just going to get 2g cosine of theta, mass of the father, mass of the daughter, and under, you're going to have the length that did not cancel here, mass of the father, mass of the daughter, and then the whole mass over 3. And that will be the angular acceleration. And if we had numbers, it's here that we will substitute the numbers and get a numerical value. All right, so a little example of how to deal with angular momentum. We'll do more examples in class.